Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Ethan, lead tutor for chemistry and biology, and in today's video we'll explore ideal gas laws. Let's get started. First, we'll look conceptually at the ideal gas law that can be used to derive the 4 individual gas laws. Then we'll learn 2 of the 4 individual gas laws and some of their application. What is the ideal gas law? It's nothing but an equation that should describe how gases will behave. The equation is PV equals nRT. This equation can tell us how gases will behave as the conditions they are in change from one situation to another. Or we can predict one variable that constitutes a gas if we know all the others. The inputs for the equation are P for pressure, V for volume, N for number of moles, R for the gas constant, and T for temperature. We can use various units for pressure and volume. However, when we use this equation, we need to be in Kelvin for temperature because pressure and volume depend on kinetic energy. And Kelvin has 0 degrees as absolute zero, meaning that there's no kinetic energy or heat. Additionally, you will always want to use moles because the gas constant has units of moles most of the time. Here's a dimensional analysis of the ideal gas law. It's important to understand the units so we know how to use the equation. We have pressure, which has units of force per unit area. For volume, we have any measurement of length cubed. N is number of moles. R is the gas constant, which has units of joules per mole Kelvin, and temperature with units of Kelvin. Next, we can substitute in Newton per meter squared for pressure, meter cubed for volume, and Newton meter for joules. When we simplify this, we see that on the left-hand side, meters squared cancels with meters cubed to leave just meters. On the right-hand side, moles cancels and Kelvin cancels. Then we're left with Newton meter is equal to a Newton meter, which is true. Of course, we can simplify this to 1 equals 1, but it really isn't necessary. Here the goal was just to check that all the units check out, and we really do have a statement of equality. Now that we know the units, we can look at how each variable changes in relation to one another. The first thing is that R will not vary. It's just a constant. So we really only have 4 variables. Where these variables are located can tell us how they're related to one another. Variables on opposite sides of the equation are directly proportional. This means that if you increase one while holding 2 others constant, the 4th variable will also increase. For example, take P in relation to N or T. If we keep V and N constant, but increase P, then T has to increase to account for the increase in P. Also, if we keep V and T constant, but increase P, then we know we must increase N to account for the increase in P. Conversely, variables on the same side of the equation are inversely proportional. Let's use P and V. If we keep everything on the right-hand side constant, but increase V, then P will have to decrease to account for the increase in V. So the takeaway here is that we can increase volume to decrease pressure, or increase temperature to increase pressure, or increase number of moles to increase pressure, and so on. Let's go through a quick example using this equation. Here we're given some volume of 10 grams of neon at 300 millimeters of mercury and 40 degrees Celsius. And the question is, what must be the volume? First, let's write down what we're given. We have a mass of 10 grams, a pressure of 300 millimeters of mercury, and a temperature of 40 degrees Celsius, and we're trying to find volume. Always take a moment to write out what you're given and what you're looking for. Now we need to get everything in the correct units. Instead of grams, we need number of moles. We can get moles from grams by dividing the number of grams by the molar mass of neon. This gives us 0.495 moles of neon gas. Next, we need our units of pressure in ATM instead of millimeters of mercury if we want to use the gas constant value of 0.082. This conversion factor is 1 ATM for every 760 millimeters of mercury. So 300 millimeters of mercury divided by 760 gives us 0.39 ATM. We also need to convert Celsius to Kelvin. Here we know that to go from Celsius to Kelvin, we can just add 273. Next, let's rearrange our equation for volume and plug in our variables. Here I'm using the gas constant value of 0.082 because it has the units of liters atm per mole Kelvin. And all those units match our units for our other variables. For our final answer, we end up getting a value of 32, and our units are in liters. So we've seen that we can predict the value of one variable given the values of the others for one given situation. But what if we want to predict how things will change from one situation to another? We can simply rearrange our equation and label it to indicate two different situations. If we divide both sides of our equation by nt, we get PV over NT is equal to R. Now we can set PV over NT equal to itself and specify situation 1 and situation 2. From here, we can actually derive all the 4 individual gas laws that we'll see in the next slides. This is the first of the individual gas laws. The Gay-Lussac law states that pressure is directly proportional to temperature when volume and number of moles are kept constant. In other words, if you have a fixed volume container with a constant amount of gas, if you increase the temperature of that container, the pressure will increase. This is because higher temperature is the same as higher average kinetic energy. With more kinetic energy, gas particles are traveling faster and colliding into one another and the walls of the container with greater force. This means that there's higher pressure. Like stated previously, the Gay-Lussac law says that by increasing temperature, you increase pressure if volume and number of moles are kept constant. So the equation for this is P1 over T1 is equal to P2 over T2. We can derive this from our ideal gas law. P1V1 over N1T1 is equal to P2V2 over N2T2. If we cancel out V and N, since those are kept constant, we get our equation P1 over T1 equals P2 over T2. Let's solve a problem using this law. We have helium gas occupies a 20 degrees Celsius box with a pressure of 3 atm. The box increases to 35 degrees Celsius. What is the new pressure? Well, we're given an initial condition, a change, and we're asked to find a final condition. Our temperature, T1, equals 20 degrees Celsius. Our initial pressure, P1, equals 3 atm, and our final temperature, T2, is 35 degrees Celsius. Let's convert our temperatures to Kelvin first. Then, since we only have temperature and pressure here, that should signal to us that we need the Gay-Lussac's law because it involves just temperature and pressure. Next, we can write out our equation, rearrange it for the final pressure, P2, and plug in the numbers. So here we get 3.1 atm. Let's just do a quick reality check on our answer. We know that we increase the temperature, so we should expect a proportional increase in pressure. And that's what we see. We went from 3 atm to 3.1 atm, so our answer is reasonable. The next gas law is Charle's law. This one states that temperature is directly proportional to volume when pressure and number of moles are kept constant. So if you have an adjustable volume full of gas and you heat it up to maintain constant pressure and amount of gas, the volume must increase. Here is the equation for Charle's law. It is V1 over T1 equals V2 over T2. Again, we can derive it by just using the ideal gas law equation, but eliminate P and N since those are kept constant, and we get the correct equation, V1 over T1 equals V2 over T2. Here's an example problem using Charle's law. We're given a sample of carbon dioxide in a pump with a volume of 25 milliliters at 37 degrees Celsius. When the amount of gas and pressure remain constant, find the new volume of the carbon dioxide in the pump if temperature is increased to 67 degrees Celsius. So our V1 is 25 milliliters, T1 is 37 degrees Celsius, N and P are kept constant, and V2 is what we're looking for. Let's convert our temperature to Kelvin, and since we only have volume and temperature, we know that it's going to involve Charle's law. We can rearrange our equation for V2, plug in, and solve. Here we get a new volume of 27 milliliters. Again, we really should do a reality check. We increase the temperature, so the volume should increase. we went from 25 milliliters to 27 milliliters, so we're good. Here are some good resources for all things related to the ideal gas law and the 4 individual gas laws. The link is provided in the description box below. It has various different units that you can use and values of the gas constant depending on what units you're given. Here's a picture of what's given in the link. You can see all the potential units for pressure and volume, as well as their conversions. Also on the top right are the values of R for different units. Also be sure to check the description for the second video in this series covering the ideal gas law. In that second video, we'll learn the last 2 of the individual gas laws as well as a more complicated example. Here are the references for the images used in this video. Thanks for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center and follow us on social media. See you next time.